Welcome to a deep dive into the world of AI agents that can use computers just like we do.
Yeah.
Imagine AI effortlessly navigating websites, scheduling meetings, or even writing code based on your instructions.
Ah.
We're dissecting a research review of 86 papers on instruction-based computer control agents.
Okay.
Buckle up. It's going to be a wild ride.
Yeah, it's a rapidly growing field, especially with the rise of large language models.
Right.
We'll uncover how these agents work, their unique challenges, and the implications of letting AI loose on our computers.
Okay, let's unpack this. You're diving into the world of computer control agents, or CCAs.
Right.
These are AI systems designed to use computers just like you do through the same interfaces you interact with every day.
Mm-hmm.
How do they even begin to grasp what's happening on the screen?
It's not about grasping in the human sense.
Right.
These agents operate on data.
Hmm.
They receive an observation of the computer's state,
Okay.
process, it's a sign on an action, and that action changes the environment, leading to a new observation. Okay, it's a loop.
So it's like a constant feedback cycle.
Yeah,
But how do they see the environment in the first place?
right.
Do they have little AI eyes peering at our screens?
Not quite.
Okay.
The research explores various observation spaces.
Mm-hmm.
The most intuitive is image screen representation,
Okay.
essentially that process screenshots.
Oh, wow.
But don't think they're limited to your tiny human field of view.
Right.
They can analyze an entire web page at once.
That's wild. But websites are built on code, right? Can't they tap into that instead of just looking at pixels?
They can.
Okay.
That's textual CERN representation.
Okay.
Using code like HTML
Hmm.
or UR hierarchies.
Yeah.
It's like accessing the blueprint of a website instead of just the facade.
That's like a more direct route to understanding what's going on.
Yeah.
So what are the advantages of that approach?
Well, textual representation can reveal hidden information like drop-down menus
Right.
and expose the relationships between different elements.
Okay.
It often includes semantic information,
Oh.
giving the AI clues about an element's purpose.
So why even bother with screenshots if code gives you so much more?
Well, code have its drawbacks.
Okay.
It can be verbose,
Mm-hmm.
inconsistent, and visually similar elements might have vastly different code underneath.
Right.
A button might look like a button to you,
Yeah.
but to an agent analyzing the code, it might look like something else entirely.
So it's not a perfect system. What happens when they encounter visually similar components? How does the text representation deal with things that look almost identical but function differently?
That highlights a key limitation.
Okay.
Text lacks spatial information.
Right.
It might struggle to distinguish between two buttons that look identical, but perform different actions.
Right.
Image representation provides that visual context.
Okay.
Like how you intuitively know the difference between your send and delete buttons based on their position.
So each approach has its blind spots.
Yeah.
What about combining them?
Some agents use bimodal representation, merging image and text. Potentially powerful, but it's unclear if it truly leads to better performance.
Right.
Could be too much information for the agent to handle effectively.
Like overloading their digital senses.
Right.
Is there anything else they use to understand their environment?
There's also indirect observation
Okay.
where agents don't directly perceive the screen. Instead of they take actions to gather specific information. Like a
Okay.
command to read a file or pulling data from an ATI.
Okay.
It's less about of seeing
Right.
and more about strategic information retrieval.
Okay, that's a bit more abstract.
Right.
Now on to acting.
Okay.
How do these agents actually interact with the computer?
Well, several approaches exist, each with pros and cons.
Right.
The most common mirroring human behavior is mouse touch and keyboard actions.
Right.
They can click,
Okay.
scroll, type.
Right.
Basically everything you can do.
That makes me wonder, how does the agent actually decide where to click or what to type? It can't just be random, right?
For clicking,
Oh, okay.
it boils down to predicting screen coordinates.
Okay.
Think of it like dividing the screen into a grid, and the agent has to pick the right square.
Okay.
Some use discrete predictions, picking from a set of grid positions.
Okay.
Others use continuous values,
Oh, they're-
allowing for finer control.
So they're learning to aim in a digital space. What about typing? That's got to be way more complex.
Most rely on language models to generate text.
Right.
The implementation varies. Some generate free text based on the instruction, while others select from predefined fragments
Right.
or extract text directly from the instruction.
Fascinating. It's like they can either improvise or follow a script. What about other keyboard actions? Are they just limited to clicking and typing?
Not at all.
Okay.
They can use shortcuts like select all,
Okay.
copy paste, and even navigate with arrow keys
Wow.
It's about mimicking the full range of human interaction.
So they're not just clicking around blindly. What other ways can these agents act on the computer?
Some agents leverage direct UI
That's
access,
it, right.
interacting with specific elements based on their IDs or XPath.
Right.
It's like knowing the exact address of a button and
Mhm.
clicking it directly
Okay.
without needing visual cues.
Sounds incredibly efficient, but I'm guessing there are limitations.
Of course, it requires the interface to be accessible and identifiable.
Right.
Often it's limited to actionable elements like buttons or input fields,
Right.
as opposed to static elements like text or images.
Right. It's a trade-off between speed and flexibility. What about actions tailored to specific tasks?
That's where task-tailored actions come in.
Okay.
Actions designed for a specific domain or task,
Hmm.
like find on page for browsing or go to home screen for a mobile device.
Right.
Highly efficient, but less generalizable.
So specialized tools for specific digital jobs. Anything?
Ready for this one?
Okay.
Some agents generate executable code to control the environment.
Wait, they can write code.
Yeah,
How is that even possible?
they can generate code using various programming languages and APIs depending on the task and environment.
Okay. Some use foundation models pre-trained on APIs like Selenium WebDriver for web browsers. Right. While others use specialized models or generate custom code through prompts. That raises a lot of questions for me. How does an AI even begin to write code? What kind of code can it generate? And what about the potential risks of giving AI that kind of power on our systems?
It's a valid concern.
Yeah.
And we'll delve into those risks later.
Okay.
The research is still evolving,
Yeah.
and there's much debate about balancing the potential benefits with the risks. But first, let's look at the brains behind these operations.
Okay.
How are these agents designed and built? There are two main approaches, foundation agents and specialized agents. Foundation agents leverage powerful pre-trained models like GPT-4, relying on their broad knowledge and ability to learn in context. They can often perform surprisingly well right out of the box.
So they're like those gifted students who just get it without breaking a sweat. What about the specialized agents? What sets them apart?
Specialized agents are more like custom-built machines using architectures specifically designed for computer control.
Right.
They employ techniques like reinforcement learning, where they learn through trial and error,
Okay.
or behavioral cloning learning from human demonstrations.
It's like the difference between a generalist and a specialist, each with their own strengths. Are there any other key differences between these approaches?
One distinction lies in how they handle information from the past foundation agents, typically use a history-based approach, maintaining a record of past observations and actions, like a digital memory.
Right.
Specialized agents often employ a state-based approach, creating an internal representation of the environment, similar to how we build a mental model of the world.
So it's like comparing a running commentary to a mental map. Interesting. But if these foundation models are so smart, do they even need to learn how to interact with specific environments? It seems like they should be able to figure it out on their own.
That's a key question researchers are exploring. While foundation models boast impressive out-of-the-box capabilities,
Right?
they often struggle to adapt to unique interfaces or workflows. Think of a master chef unfamiliar with the layout and appliances of a new kitchen. They might eventually adapt, but it won't be smooth sailing.
So even the most brilliant AI needs some hands-on training. How do they actually go about learning these environment-specific skills? Walk us through the training process.
There are a few different approaches. Reinforcement learning is one where they learn through trial and error,
Right.
receiving rewards for successful actions and penalties for unsuccessful ones.
That trial and error approach is just one method. They can also learn by observing how you interact with the computer, right?
Precisely.
Okay.
Behavioral cloning involves training agents on datasets of human-computer interactions,
Mm-hmm.
allowing them to learn by example and mimic actions leading to task completion.
So it's like they're shadowing an expert user. Are there any other ways they can learn and improve?
Some agents utilize long-term memory storing successful experiences for later retrieval. It's akin to building a mental library of best practices, drawing on that knowledge when faced with similar situations.
So they're not just learning from scratch each time they're building on their past successes, but where do they get all these experiences to learn from in the first place? What kind of training data are we talking about?
They're trained on datasets designed specifically for computer control, and these datasets come in two main flavors: controlled environments and offline datasets. Controlled environments are artificial simplified settings offering a safe space for experimentation without real-world consequences.
So they're like digital playgrounds for AI. What about the offline datasets? What makes them different?
Offline datasets are created by recording human interactions with real-world systems. It's like watching hours of footage of people using computers and then extracting the patterns and strategies from those observations. These datasets offer a more realistic training ground, but also present greater challenges due to the inherent complexities and inconsistencies of human behavior.
So they're learning from the messy reality of how we actually use computers. That makes sense. But are these datasets limited to just one type of computer environment, like web browsing or mobile apps?
You're right to point.
Oh, hey there. How can we help?
There. So what's the best strategy for the computer use agents?
That's a great question. It's not about one best strategy.
Yeah, it really depends on what you want the agent to do,
Okay, let's unpack this. If you want an agent that can learn a broad range of tasks,
right?
then you might want to focus on pre-trained foundation models.
Like the super smart AI we talked about earlier.
Exactly. These models can leverage their existing knowledge and quickly learn new skills.
That makes sense.
But if you need an agent to perform very specific tasks in a particular environment,
Then specialized agents might be the better option.
yeah, these can be custom built for a specific purpose, optimizing for it.
So it's about finding the right tool for the job.
What's fascinating here is that the best strategy might actually be a mix of both,
Oh, interesting.
combining the general knowledge of foundation models with the specific expertise of specialized agents.
That makes sense.
It's also important to consider the learning strategy.
Like how they actually learn to act.
Right. Do you want them to learn by trial and error or
Okay.
by observing human behavior?
It's like choosing your own adventure, I guess.
Yeah, and the best choice depends on the specific context of the task.
Okay, so there's no magic bullet then.
Not quite. There are many factors to consider, and the field is constantly evolving.
Right, and we'll talk more about those factors, like evaluation methods next.
Exactly. So that being said, let's continue where we left off, which was,
Yeah, about the training data sets.
right, we were talking about the limitations of only training on web browsing data.
Oh.
We see a lot of data sets focusing on web browsing, followed by Android devices, and then personal computers.
I could see how that could be a limitation. Wouldn't it be better to have data sets that cover a wider range of environments to create more versatile agents?
Absolutely. As these agents become more capable, we need more complex and diverse data sets to truly push their limits. Think of it like training an athlete. You need to constantly increase the difficulty and variety of their training regimen to help them reach their full potential.
So the training data needs to evolve alongside the AI's capabilities. It's a constant game of catch-up. But how do we even know if these agents are truly learning and improving? How do researchers measure their skills and progress?
That's where evaluation comes in, and it's not as simple as grading a test. We need to consider not just whether they can complete a task.
Oh yeah, let's hear it.
Thank you for your explanation.
That's a really interesting way to put it.
Yeah, it's almost like we're witnessing a new form of